Rocket science is the stuff of legends, powering humanity's leap to the stars. But what if I told you that understanding rocket propulsion doesn't have to feel like deciphering alien hieroglyphs? I mean, what's the best way to learn something? Make it. But unfortunately for all of us, real rockets aren't for practice. At its core, rocket propulsion truly is simple. Newton's third law of motion. For every action, there's an equal and opposite reaction. So when a rocket expels high-speed gases in one direction, it uses this to propel itself in the other. But if it were that easy, it wouldn't be called rocket science. So the devil truly is in the details. Let's dive into this technological magic together. Newton's third law of motion forms the bedrock of rocket propulsion. Imagine you are standing on a skateboard and you're throwing a really heavy ball forward. As you release the ball, you are pushed backwards. Rockets operate similarly, except instead of throwing a ball, they release high speed exhaust gases generated from burning fuels. This exchange is quantified by thrust, the force propelling the rocket forward. Mathematically, thrust is given by the above equation, where m dot is the mass flow rate or how much propellant is being expelled per second, which is measured in kilograms per second. Ve is the exhaust velocity or the speed of the expelled gases relative to the rocket, measured in meters per second. Pe is the pressure at the nozzle exit, Pa is the ambient pressure, and Ae is the nozzle exit area. Specific impulse is a critical measure of a rocket's engine efficiency. Think of it as a liters per kilometer of a car, except it's measured in literally seconds. Specifically, it quantifies how efficiently a rocket uses its fuel to create thrust. The higher the specific impulse, the more fuel efficient the engine is. This especially comes into play on longer space missions, where the slightest bit of weight can complicate everything. The formula for specific impulse is as given here, where g naught is the standard gravitational acceleration, approximately 9.81 meters per second square. While efficiency and thrust are vital, so is understanding how much velocity is required for a rocket to complete its mission, whether it's going out of orbit or traveling to Mars. This is where the Tsiolkovsky rocket equation comes in. Derived by the Russian scientist Konstantin Tsiolkovsky, it describes the relationship between a rocket's velocity change, delta V, its initial mass, and its final mass after expelling fuel. In the equation, m naught is the rocket's initial mass, including fuel, and mf is the rocket's final mass after fuel is expended. Ln is the natural logarithm function. This equation reveals a harsh reality. The more fuel you carry, the more heavier your rocket becomes. And the heavier your rocket becomes, the more fuel you need to lift the fuel. This compounding problem, known as the tyranny of the rocket equation, keeps engineers obsessing over mass reduction and efficiency. Rocket propulsion isn't just about equations. There are many factors that weigh in when we build a rocket. Propellants can be solid, liquid, or hybrid. Liquid propellants like liquid oxygen (LOX) and kerosene (RP1) are common in modern rockets. The combustion chamber, the heart of the engine where fuel burns, producing high pressure, high temperature gases. And finally, the nozzle, which shapes the exhaust flow to maximize velocity, converting thermal energy into kinetic energy. This whole time, we have mentioned efficiency a lot. Why does it really matter? Imagine driving across the country in a car that guzzles fuel and has a tiny gas tank. You'd be stopping constantly to refuel, and this makes the journey really frustrating and inefficient. In space travel, we do not have the option of stopping mid journey and refueling, at least not yet. This is why engineers design engines with the highest possible specific impulse and optimize spacecraft mass to achieve space missions without extra fuel. In conclusion, while the physics of rocket propulsion may have started with the simple Newton's action reaction principle, the real complexity lies in managing efficiency, velocity, and mass to overcome space challenges. By understanding all these principles, we can actually appreciate the ingenuity that go behind making our rockets soar out of the atmosphere. For my project, I used Rocket Propulsion Analysis, RPA for short. It's like a playground for rocket nerds. This is the input page in RPA, and by inputting parameters like fuel properties, chamber pressure, and nozzle dimensions, I could simulate engine performances. I tested three engines: the RD275, the RL10A33A, and the ASTIS. And each of them have unique features as well as provide us with unique results. So let's get into it. RD275 uses UDMH and N2O4 and achieves an efficiency of 96.72%. Its efficiency reflects its advanced engineering for high thrust to weight ratios in atmospheric launches. It achieves the highest thrust, making it ideal for heavy lift applications. However, it has a lower specific impulse that indicates higher fuel consumption for a given thrust. RL10A33A with liquid hydrogen and oxygen is slightly less efficient at 95.98%. The slightly lower efficiency is likely due to its design complexity for maximizing vacuum performance. It has the highest specific impulse, making it the most fuel efficient engine. However, its thrust is relatively low, meaning it's suitable for upper stage applications where efficiency is prioritized over raw power. The ASUS shows the lowest efficiency of 94.76%, possibly due to its reliance on hypergolic fuels, which, while reliable, are less energy dense compared to cryogenic fuels. The lower combustion temperature in the ASTIS contributes to lower thrust but makes it more manageable in terms of thermal stress on components. These are my key findings and what I learned about each engine. These simulations also gave me insights into how engine design and fuel choice impact performance. If you want to know more about the process as well as more results, do check out my article in the description down below. Was this easy? Not at all. The software took a lot of time to learn, and every simulation needed a lot of attention to detail. But it also taught me that persistence eventually pays off, and that precision is non negotiable in aerospace engineering. However, this project is just the beginning. From exploring advanced propulsion systems like hybrid and electric systems to integrating AI for better design, the future is full of possibilities. As I continue this journey, I hope this work continues to inspire others to explore the wonders of what rocket science is. So, whether you're a space enthusiast or a budding rocket scientist, I hope this video showed you that propulsion is not just about equations, it's about igniting curiosity and reaching for the stars. If you like this video, be sure to check out my article in the description down below, where I share more of my discoveries and insights and more about the simulation as well. And if you like this video, be sure to give it a like and subscribe to me to stay tuned. Bye!